Section 7.7 is exponential growth and decay. I can model exponential growth and decay. Big idea for this section. An exponential function can model growth or decay of an initial amount. Take note on page 460, has exponential growth. Exponential growth can be modeled by the function y equals a times b to the x power, as long as a is greater than 0 and b is greater than 1. This part right here is important for exponential growth. The base b is the growth factor, and it equals 1 plus the percent rate of change expressed as a decimal. And the reason, guys, that it's 1 plus our decimal here is because 1 is the same as 100%, but when we write it as a decimal, remember we get rid of our percent sign. And since we got rid of our percent sign, we move away, and it's 2 places away. Percent means per 100, so we divide by 100, move it 2 places. So this 1 here just means 100% of the original part. And because we're growing, we're going to plus, so add the percent rate of change, but we put that in as a decimal. Our A is where we start, and our B is our growth factor. And we get that again by taking 1 plus our percent rate of change, but we write that as a decimal. Example 1 here says, since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. If the trend continued, about how much was spent at restaurants in 2015? So here, we're talking about exponential growth. It's increasing by the same amount each time, but it's a percentage, which means we have to multiply. So here, because we're multiplying by the same amount each time, we said that means it's an exponential function, and we're going to use our exponential model here. A times b to the x power. Remember, b is our growth factor, and we find that by taking 1 plus, because it increased, 7%, but that 7% we put in as a decimal. So to get rid of my percent sign, I move my decimal 2 places, and I get 0.07. So b, or my growth factor, is going to be 1.07. A is my initial amount, which here is 360 billion. So y equals 360 times my growth factor, and we raise that to the x power. This is the function I'm going to use for this problem. Now, we want to know how much was spent at restaurants in 2015. Well, x is my time. It says each year. So in terms of years here, if I have 2015, and I started in 2005, to find that difference, we subtract and get 10. So my x value here is going to be 10. So I take 360 times 1.07 raised to the 10th power. Remember, that's an exponent here, guys. And I'm going to get approximately 708, and then that's in billions of dollars. Approximately $708 billion was spent at restaurants in the United States in 2015, according to this pattern. In part B here, it wants the expression that represents the equivalent monthly increase of spending at U.S. restaurants in 2005. So here, we're talking about our growth factor. The increase is our growth factor. And here it was 1.07 to the x power, but this is in terms of years. Okay, we want in terms of months. So what I'm going to do is I'm going to take 1 plus my percentage, but remember that this is a yearly percent. We don't want yearly, we want monthly. And 1 year is 12 months. So instead of having a full year, I'm going to divide it by 12 to give me how many months, how much it is per month. Now, because I changed that to monthly here, I also have to change my exponent to be in terms of months. So again, 12 months in 1 year, which means the number of years are x, we have to multiply by 12. And that's going to give us how many months we have. So here, 1 plus, when I take 0.07 or 7% divided by 12, I get approximately 0.0057. and I take that to the 12x power. 12 times x here is in years. So when I add those up, I get 1.0057. And if we want to, I can change my exponent to just be an m for months. Just make sure that you define that. So I can either leave it as 12 times x, with x being in terms of years, or I can change it to m as long as m is months. Either one of those works. Regardless, we're going to combine that to be 1.007 or 57, but we can leave it as 12x in terms of years or m for months. Feel free to pause here and give this a try if you'd like. Now, suppose that in 1985, there were 285 cell phone subscriptions in a small town. The number of subscribers increased by 75% each year after 1985. How many cell phone subscribers were in the small town in 1994? So here, again, we're going to start off, because we're multiplying by a percent, it's going to be an exponential function, a times b to the x power. When we find the percent, we multiply, and since we're repeatedly multiplying, we have to use an exponential function. Here, our original amount was 285. And my b factor, or my growth factor, I take 1 plus my rate of change as a decimal. And 75%, I get rid of my percent sign. And since I'm getting rid of my sign, I move away from it, 0.75. So my growth factor is going to be 1.75. So times 1.75. And here I raise that to the x power. And this is the function that I'm going to use. Now, we need to figure out, it says per year, each year here. We need to figure out how many years. I have 1994 now, or at the time, minus where we started, 1985. And that's going to give me 9 years. So 9 is going to be what I plug in for x. Y equals 285 times 1.75 raised to the 9th power. Here, this gives me approximately 43,871.99 subscribers. But since we're talking people, guys, we're going to round that up. 99 rounds up here. 43,872 subscribers, because our subscribers, we're talking about people here. So we round to the whole number. When a bank pays interest on both the principal and the interest an account has already earned, the bank is paying compound interest. And we represent it by the formula a equals p times 1 plus r divided by n to the nt power. Here, guys, this is very, very similar to the formula that we've been using for exponential growth, especially in the problem where we had to switch from yearly to monthly. So a here is our initial amount, and p stands for principal, which is our initial amount of money. Our b is our growth factor, and we take 1 plus our rate. And here, we're taking 1 plus our rate. We're just dividing it by our number of terms. And we had to do that before with our growth factor when we were talking about the restaurant problem, and we had to get it to monthly. Same idea. And when we did that, we took our exponent and multiplied by 12 as well to get it to monthly. How many times per year we were doing that? Same thing here. So n is our number of times per year that we're compounding it. And instead of an x, we just have t, because in compound interest, we're always talking about time, which is usually what we're talking about in exponential growth. But here it's always going to be in years, so time in years. So again, very, very similar formula. This one is just a little bit more set up to work with the money pieces. So principal per p, r is our interest rate. We still put that in as a decimal. N is our number of times compounded per year. So that's where we would change it if it was monthly or quarterly or semi-annually into how many of those we'd have a year. And t is our time in terms of years. So in example 2 here, we have compound interest. Suppose that when your friend was born, your friend's parents deposited $2,000 in an account paying 4.5% interest compounded quarterly. What will the account balance be after 18 years? So here, our account balance, A, equals principal times 1 plus our rate divided by the number of times it's compounded raised to the nt power. Number of times it's compounded times number of years. And we can plug in what we know. We know principal is how much money we started with. We know our interest rate is 4.5%, but again, we enter that as a decimal. So I get rid of my percent sign and move my decimal 2 away. So it's 0.045. My number of times per year is quarterly, and there are 4 quarters in a year. And my time here is 18. And again, my N is the same here, and it's based off it being quarterly and 4. It says, what will the account balance be? We're looking for the account balance, which is our A value. So when I read my equation, I have A equals P 2000. My 1 doesn't change, nor does my plus. My rate is the 0.045 divided by N is my number of times per year, which here we said was quarterly, 4. And then I use that 4 in my exponent as well, because if I do it 4 times per year, I have to take how many times per year times the number of years. And that gives me the total amount of times that is compounded. And if I were you guys, I would go ahead and multiply that right away. Otherwise, when you type it in your calculator, you're going to have to put a parentheses here. And sometimes you're going to forget that and get the wrong answer. So a couple big things here. Again, you're going to want to make sure to have those parentheses. You're also going to want to make sure that you put this in as a decimal. Don't forget to do that. It's going to make your answer seem pretty big and unrealistic. So from here, we just type this right in our calculator. Make sure we put in our parentheses here too. We just type it in exactly as it's written. 2000 parenthesis 1 plus 0.045 divided by, you can't put this in as a fraction, guys. You have to use divided. Your calculator won't let you put a decimal in a fraction. So divide by 4, parenthesis. We use the little raised to guy there for the exponent. It's over 1 up 1 from the 7. If you have the normal 2-line calculator, to the 72nd power. And here, we are going to get our account balance to be approximately $4,475.53. Now, feel free to pause here and give this one a try. Same situation, same principle. The only difference here is that it's compounded monthly. We still want to know what is our balance going to be after 18 years. So A equals P times 1 plus R over N to the Tn power. You're going to want to know that formula. Okay, you're going to want to know that formula. Our original amount was 2,000. Our interest rate was 0.045, 4.5%, divided by monthly here, though, is going to give me 12 times per year, 12 months in a year. So as far as my time goes, I take that 12 times the number of years, 18. And that's going to give me my balance, account balance, A. Again, here, you're probably going to want to multiply here first, and then plug it in. If you don't, you're going to want to put this in parentheses. So either way, we can either multiply the 12 times 18 first, or we can plug it in parentheses. So we either put the 216 or parentheses. Either way, when we do this, we are going to get 4,489.01. Those of you listening should plug that in just to make sure you can get it. There's a lot of steps to typing that in your calculator. If you can't, find me and I will help you. So if we look here, guys, it is just a little bit different. We made a little bit more money by compounding it monthly, and that's because when we have interest calculated more often, we get more interest based off the interest faster, and so it builds a little bit more that way. I'm going to pause this video, stop this video here, and continue on in another one.